we go. Okay, that way, and I haven't done it up till this point, if you are away, you will be able to catch up if you want to by watching whatever we did as our lesson. Yes? Okay. As I was saying, there's a whole bunch, Jude? Electrons are, what am I saying? There's a lot of black diamond stuff, okay? Black diamond, black diamond, black diamond. Mostly what you need to know about this is that it is called the electron cloud model, and you don't need to know much beyond what Tyler taught us before about this model, and that is that what do the electrons do in the electron cloud model? Tell your partner, what do the electrons do in the electron cloud model? What do they do? What do those electrons do? They buzz around the nucleus like a hyperactive fly, okay? Okay, so that's the general idea behind it. Okay, but we're going to watch a video. Hopefully it will come up in just a moment here.
Let me show you how to quickly open one.
Why is it, I hope this is an ad.
Go to shopify.com and start a free trial.
No, I don't want to do Shopify. Oh, skip ads, yay. Okay.
Quantum mechanics and the shape of atoms.
Oh, now we need to press pause because I need to get our sound on. Sound. Hello. Everything's a little slow this morning, including me. I'm feeling really tired and slow this morning. I don't know about you, but it's very much a Monday morning for me. They are hard. They are hard. Okay, now this guy talks fairly quickly, but remember, you're just trying to get the overall idea of it. It's to show you that what we are learning about the atom in grade 9 is a very simplified version of what's really happening, okay? But you don't need to understand it. And in fact, most people, even people with degrees in chemistry, don't actually really truly understand what's happening here. I'm not sure that Bohr understood what was happening here, for example. He was not happy about it. Neither was Einstein. So if they're not super happy about it, then if we don't really understand it in a true, like, deep way, that's not surprising, okay?
By Schrodinger. We all know about quantum mechanics.
Quantum mechanics and the shape of atoms as discovered by Schrodinger. We all know about quantum mechanics, which is of course the physics theory that describes atoms and elementary particles, how they move around like slushy little waves, and interestingly, it predicts what they look like, what shape they have. It was invented in the first couple of decades of the 20th century by a lot of people all working together. Amongst them were Planck, Heisenberg, Bohr, Davison, Du Bois, Einstein, and of course Schrodinger. These guys already knew a lot about atoms from the scientists who came before them. For instance, they knew that there are about 100 different atoms in nature, and that these atoms join in larger structures such as molecules, metal lattices, and salt lattices to make everything we see around us. But what they didn't know, what exactly was going on the inside of the atom, what it was made of, what shape it has. So they were doing experiments on that. And pretty soon they found out that atoms themselves are composed of smaller particles. They found the proton and the electron, and they were theorizing the neutron. And with the protons and neutrons, they almost immediately knew what the deal was. They realized that they were clumped in a very tiny core at the center of the atom. That core was really small. A typical atom is about 300 picometers.
What do we call that little tiny core of the atom? What's it called? Nucleus. Everyone, what's it called? Nucleus. And what two particles are in the nucleus? Protons and neutrons. Excellent.
Whereas the core is typically 0.01 picometers. So this leaves this big open space in an atom, and they realized that this open space was going to be the domain of the electron. But what they didn't know was exactly how the electrons are filling this space, if they are spinning around or orbiting or what. So they made an initial sketch. They called it the planetary model of the atom, basically the core at the center and the electrons spinning around in big orbits. It was their first idea of what an atom looks like. It proved to be incorrect, but it was a fine enough starting point. It made some very nice predictions, and it allowed them to start doing experiments, and they did. One man who was looking at these experiments was a Frenchman called Dubreuil, and he was noticing something very interesting. He found that when electrons were forced to interact with matter, either through some physical process or by hitting a detector, that the electrons presented themselves as particles, as hard little balls of matter.
So this is the first thing. When they were actually looking at an electron, making it, hitting it with a photon, doing something to it, or firing an electron at a detector plate, the electrons behaved like what? Like a particle. And that makes sense. We know that electrons are subatomic particles. So this makes sense, yes? Yeah. However, just wait, it gets weird.
Kind of what you expect them to do. But when the electrons were
allowed to move on their own, either by being shoved through a crystal or allowed to wander through a vacuum, they always propagated as if they were waves. It was almost as if when you stopped messing around with the electron, it would suddenly fall apart into some sort of wave function, some sort of probability wave that sloshed around all of space and predicted where the electron was likely next to be found.
Okay, so this is where it gets weird. So when you're not looking at it, when you're not having that electron interact with something, it ceases to be a particle and it becomes this sloshy wave-like thing, which is a probability field of where you might find the electron. So if this is our probability field, then our electron is somewhere within here. So maybe you take a photograph of it, you interact with it, and when you interact with it, it becomes a particle, and maybe it's here. And the next time you look at it, maybe it's somewhere else. So this is why I say it's really strange. Okay.
This was the first time they encountered
particle-wave duality in matter, and it spelled disaster for their planetary model. Because this model really assumed that the electron stays a particle during the entire orbit and doesn't fall apart into a wave halfway through. So they needed a new model, but they realized that this model couldn't come from classical mechanics because classical mechanics makes the same assumption that particles stay particles. In fact, they would need entire new mechanics, some new theory that included the wave-like nature of particles.
Can you guess what kind of mechanics? Quantum mechanics, yes.
And this is when Schrodinger entered the picture. He had looked at the experiments as well, and he found one common theme running through all of them. In his insight, he saw one law of nature, one equation that seemed to hold no matter what you did. He called it the wave equation. Now,
that wave equation appeared in my first year chemistry textbook, scared the snot out of me. Holy mackerel, I saw that thing and I was like, what? Okay, is that not crazy? Uh-huh. Now, just wait, because then they start to do things with this equation.
Nowadays, we simply know it as the Schrodinger equation because it was the rock-solid core onto which all of quantum mechanics was built. Schrodinger realized that with this equation he was now in a very interesting position. What he could do is take an atom, any atom, Take its properties, stuff like its mass and its charge, all those numbers, put that in that equation, do the math on it, and what he would end up with would be a series of pictures that showed what that atom looks like. He went on and did it for hydrogen, which is the easiest atom, it's just one proton, one electron, and that one proved to be crucial into unlocking the shapes of all the other atoms. And when
Okay, literally when he says do the math, all of that math, that is the math that they do. We didn't have to do that in first year chemistry, but yeah, but holy moly. Seems unlikely. But anyway, he came up with.
When he had worked his way through the math, these are the pictures he found. Ladies and gentlemen, the shapes of hydrogen.
Okay, so you know how we think of the atom as like this lovely little sphere, or like the nucleus with the little electrons going zipping around the outside? No. The electron clouds take these shapes. The nucleus is still in the center, but these are the shapes that the electrons take, sort of. These are the probability fields of finding electrons. I'll let this guy talk a little bit about what a probability field is.
So this then is how an electron fills the empty space in an atom, not by spinning around, but instead with its blobby-shaped wave function, which we call the orbital. What I've drawn here each time is just the same hydrogen atom with a proton at the center, and the electron has been allowed to go into a different orbital each time by giving it energy, for instance. And if you look at this one, these three blobs together form that one orbital. They house that one single electron.
Okay, so you remember the rooms in the Bohr model? The little boxes that we had in the Bohr model? You remember those? Okay, so those can hold 2 electrons each, yes? So this one blobby shape can hold 2 electrons. And at any point in time, those 2 electrons will be found somewhere in that little blobby shape. That one's about a sphere. Okay, that one's kind of spherical. But there's another blobby shape, which is kind of like 2 spheres with a hole in the middle, a gap, and the 2 electrons are in there somewhere. Now here's the fun bit. At any point in time, you might have 2 electrons over here, and then later on you might have 2 electrons over here, but at no point in time do they pass through the space in between. The electrons never exist here, which is just weird, right? An electron is here, then it's here, and it didn't go through the space in between. And they explain that by saying when you're not looking at it, it's a wave, and that wave is this blobby shape. Yeah, and when you look at it, it collapses into one position within that blobby shape. Kind of. It's very strange.
And this one makes a fine example. We can look a bit at its properties.
What you can do in an experiment is take a hydrogen atom and prepare it in this orbital by giving it some energy, for instance. And if you leave it undisturbed, then the electron takes this shape. It becomes this wave function, this blobby shape.
So if you're not looking at it, the electron takes on this shape. It's no longer like a little speck. It's now that shape. Strange, yes?
And if you then were to take a measurement of the electron, find out where it actually is,
what would happen is this wave function suddenly collapses. It condenses into a single point, which we call the electron. If you then were to re-prepare your hydrogen atom in the same orbital, maybe give it some new energy, then you can do a new measurement, and you can find that electron in the same blob, or in any of the other blobs. And if you were to repeat this thousands of times, you would end up with a picture very much like this. Notice that there's a higher probability of encountering the electron at the center of a blob. There the probability wave function becomes more dense. But there's something interesting about these pictures, of course, something that is...
Okay, so what they're saying is that the likelihood of finding the electron in any area of this blobby shape is, the likelihood is higher where you see more dots. That's where the probability field is the highest. And where you don't see as many dots, it means the probability of finding an electron there is lower. Do you need to understand this?
No.
No. Okay.
Well, staring us in the face. The fact that these blobs are not connected. There's an area in between where you cannot encounter the electron. So it kind of begs the question, how on earth is the electron traveling from one blob to another? Is it teleporting or what? This was one of the important questions that led to 40 years of heated debate that ended up with Einstein saying very angry things about dyes. But who cares? Schrodinger had made an important discovery. He had found the shapes of hydrogen. And using that as a basis, those that came after him were able to find the shapes of all the other atoms. They are very much based on hydrogen. They use the same orbitals. It's just that the higher atoms consist of more electrons, therefore they require more orbitals to house all of them. So you end up with a situation where the orbitals all get stacked on top of one another, overlapping but not mixing. They do, however, repel, because that's what electrons do, they repel one another. So the orbitals begin distorting each other according to some very complicated math. But these guys were also good at what they were doing. And combined with Schrödinger's discovery, they had now made a link between physics and chemistry. A link which in fact led to an entire revolution in both of them. So with that, I would like to conclude.
So just before we go on, just take a note. Without these discoveries, we would not have rocket fuel, we would not have an MRI scanner, we would not have electron microscopes or string theory, or there's a whole bunch of other stuff on there. Very, very necessary stuff and very complicated.
By just saying, Mr. Schrodinger, thank you very much.
Diodes. Have you guys ever heard the word diode? You might have heard of an LED. Have you heard of LEDs, the lights? Those are light emitting diodes. Okay, so without this, light emitting diodes and computers and transistors would not have been. I know, right? Crazy. Anyway, that was kind of nice. So, you are not really responsible for any of that, other than knowing that there is an electron cloud model and the electrons are like hyperactive flies buzzing around the nucleus. But it gives you an idea of how crazy small things really are, okay? Oh yeah, it all comes down to math. And at that point, when it's all mathematics, I don't understand it anymore, okay? But, yep. Okay, so why don't we go back to something that's a little more concrete, a little more easy to understand. We're going to go to page 62. 62. And I'll turn the lights on a little bit so you can see your own paper. Now, do you guys remember, this is again getting to know the periodic table, do you remember the main group elements? Where would we find the main group elements? Are they in the middle? They're on the periodic table, but they are on the two edges of the periodic table. So the main group elements are groups number 1, 2, and 13 to 18. Those are our main group elements. It's everything in the main body of the periodic table except for the transition metals. Where would I label my transition metals? Where do they go? Yes. They go in the middle here. So we have the transition metals. Lastly, we have the Lanthanides and the Actinides. Do you remember how to figure out their names without having to memorize them? Yes. Yeah, the first element in that row is lanthanum. Okay, so this one here is lanthanum, and this one here is actinium. What do we call the vertical columns? Columns, like, so each, call those groups. And what do we call the rows? Yes? Those are our periods. Okay, so we have rows and we have rows which are periods and columns which are groups. Periods are always referred to by their number. So row 2 is called period 2. Groups are often referred to by their number. Column 14 is called group 14. But there are 4 groups that have common names. Do these names now sound a little bit familiar after last week? The alkali metals. That's group 1. Okay, and we can see them on this table here. We have the alkali metals. Is hydrogen an alkali metal? No. The alkaline earth metals, which is group 2. What's the name of group 17? Halogens or halogens. And group 18 is the noble gases. Excellent. Okay. You do need to memorize those 4 group names, where the transition metals are, where the main group elements are. Well, it says you have previously learned about the location of metals and nonmetals on the periodic table. We're going to draw the staircase that separates, because one of the things you should be able to do is to draw the staircase. So we're going to start here at the corner, top left corner of boron. Okay? And we go down, and then we go across, and then we go down and across, down, across, down, across, down, across, down. Now we are going to shade in the nonmetals. So where would I shade? To the right of that staircase or to the left of that staircase? So I would shade over here. Nonmetals. Where do I shade my nonmetals? Where do I shade my nonmetals? To the right. So my nonmetals are over here. At this point, we are totally ignoring the metalloids, okay? Totally ignoring the metalloids. And who should we not forget? Because there's another non-metal that we might have forgotten. Yes. Hydrogen, yes. Exactly. Hydrogen's its little group of 1. Do you remember what properties are? Yes. Those are the characteristics, yes. And could you please tell your partner, without looking at the little chart there, so look up from your paper, what are some properties of metals? Tell your partner some things that you know already about metals. Did you get that they were shiny? How about the fact that they are solids? Okay, metals are solid at room temperature. There's one exception. Do you guys know who is liquid at room temperature? Yeah, it's mercury. Yeah. Okay, mercury was a liquid. Do you guys know what the concept of density means? What is density? It's the amount of matter in a given amount of space. So the more matter you pack into a smaller space, the more dense something is. Yep. I'll give it to you in just a second here. So density is equal to the mass divided by the volume. So it's the amount of matter, the mass. So density we can represent with the letter D. Density is equal to the mass over the volume. Or you could say D is equal to M over V. Metals tend to be very dense compared with other elements, compared with nonmetals. Now here's some new words for you, and these are ones you do need to know the meanings. These are vocab. Malleable and brittle. Has anyone heard the word malleable before? You've heard it before, a few of you. Okay. Malleable kind of means like if you have a dough and you can squish it and reform it into other shapes, that is malleable. If you have some silly putty, you guys played with silly putty? Yeah, silly putty is malleable. You can change its shape by squishing it. If you squish some silly putty or you squish some dough, does it break? No, it does not break. So we say that it is malleable. Has anyone ever been to a place that has, sometimes there's a machine and it will take a penny or a coin and it will flatten it for you? Yeah? When I was a kid, we used to stay up on Shuswap Lake and there were train tracks there. And we did something that you really shouldn't do because it's terrible for the train, but we didn't know because we were just kids. You take a penny, which, do you guys know what pennies are? Yes? Okay, good. We would take a penny and we would put it on the train track, okay? And the train would run over the penny. And what would happen to the penny? Would the penny break? No, it would just get squashed flat. So you'd go back afterward and there's this squashed penny, but it's supposedly terrible for the train's wheels and the railing itself. So don't ever do that. I'm very sorry that I did it. I just didn't know any better. Now the opposite of malleable is brittle. Has anyone ever had peanut brittle? Yes? Okay. It's like peanuts in this sort of hard caramel stuff, and if you hit it, it just shatters. It's like glass, okay? Not as sharp as glass, but the same idea. So brittle, if you hit it with a hammer, it will break or shatter. Malleable, if you hit it with a hammer, it will deform instead of breaking. Well, I mean, honestly, you can hit metal with a hammer until it is just one atom thick, and it won't break. Nope, not metals. They just squish, squish, squish. until you get to one atom, and then you can separate those two atoms. But yeah. Ductile. Ductile is another vocab word. Ductile means it is able to be pulled into a wire. So imagine again that you have your silly putty and you begin pulling it. What does it do? It gets longer and longer and longer. Eventually it will come apart, but only because you stretched it super, super thin. But what if you took a thread and it wasn't a very strong thread, let's say, and you just pulled it like that? What would happen? It would break, okay? So things that are ductile are stretchable. You can pull them into a wire. Things that are non-ductile, they will resist pulling until they snap, so they won't stretch. Okay? Okay. And the last two, maybe you got these ones on your own. The metals are really good conductors of heat. That's why your pots and pans are metal. And metals are also very good at the conduction of electricity. That's why you have copper wires in your house. Okay. So metals are pretty easy when it comes to knowing their properties because a lot of them you just know. Metals are shiny. You know that. You can just look at a metal. You can be like, oh, look, here's a metal. It's shiny. Oh, what state is it at room temperature? It is, oh, it's a solid. Okay. Is its density high or low? That one you might need to think about a little bit more. You know, it's got a high density. You'll need to remember those new words. Cover up those words for yourself and see if you can remember the new 3 words that we just learned. One starts with an M. One starts with a B, and one starts with a D. Let people remember it on their own. Tell your partners what those 3 words are. One starts with an M. One starts with a B. One starts with a D. Yeah. Okay, so number 1, what is the word that starts with M? Malleable. And we spell it, it's like mall. Okay, so we write the word mall, and then we write E, and then we write able. Okay, so it's mal, or mall, E, able. What's the word that starts with B? Brittle. And that one's not too hard to spell. Brittle. I'll make that look like 2 T's. There we go. Brittle. And then finally, what's that last word? The one that starts with D? Ductile. And you can kind of remember that because, you know, when you go up into the ceiling and you're rooting around in there trying to find things, you might find some ducts and you also might find some wires, right? And being ductile is the ability to be pulled into a wire. We have ductile. Now, nonmetals, basically you take the metal characteristics and you just compare them, okay? So, metals are shiny, nonmetals are dull. State at room temperature, mercury is metals are solid except mercury, which is liquid. Nonmetals, now this one's a little bit tricky. They are both, there are solids, there are gases, and there's one liquid. So it's not like, no, water is not an element, it is a compound. It's made of two elements, oxygen and two hydrogens. Okay? These are all nonmetals. Okay, but it's not an element, so when we say nonmetals, we're referring to nonmetal elements. Because when you get into compounds, compounds have all sorts of different things. So, for example, the wood here is made of carbon, hydrogen, and oxygen, and some other things. And it's obviously a solid, yes? But the methane gas that comes out of our gas things is obviously, it's called methane gas. It is a gas. It's made of carbon and hydrogen. So it's really hard to predict what nonmetals will do when they're in a compound. Okay. Now, density. If metals have a high density, that means that we could predict that nonmetals will have a low density. Metals are malleable, whereas nonmetals are brittle. I want you to think about graphite. What is graphite? Do you guys know? Where would you find graphite? Yes. You would find graphite in your pencil. The pencil lead is not actually lead, it is actually graphite, and graphite is made from carbon. Now, if you imagine you've got your pencil lead and you hit it with a hammer, what happens to it? Does it smoosh or does it break? It breaks, okay? And that's because nonmetals are brittle. Okay. Also, I would like you to imagine that you have a pencil lead, maybe one that goes into a mechanical pencil, and you try pulling it. Does it stretch? If you pull it hard enough, what will happen? It breaks, okay? So nonmetals are non-ductile. The conduction of heat, what do they make your pot, when you have a pot or pan, what's the handle usually made of? Usually on top of it, there's some rubber or plastic, and the plastic on the handle is made of carbon, hydrogen, and oxygen, which are nonmetals, and so they don't conduct the electricity, or not the electricity, the heat. I can't get any words right this morning. They don't conduct the heat very well, okay? That's why if you actually have a pan and it does have a metal handle, often you will use something like cloth or an oven mitt to insulate you, and that cloth or oven mitt is made of nonmetals. And conduction of electricity, you have copper wire, but do you have just bare copper wire running through your house? No, usually what is around the copper wire? There's like a rubber sort of a thing, different colors. You'll see there's like almost like a plastic coating, okay? And again, that is because it insulates that electricity and keeps it from, like, you know, going to places it shouldn't go. Electrical tape is made of plastic and stuff. It is definitely a non-metal substance, okay? Yeah. So you are responsible for memorizing this table. And there will be a quiz on the properties of metals and nonmetals. I would like to have it on Thursday. Does that seem like enough time to memorize that table? 3 days from now, Thursday. Yep. Monday, Tuesday, Wednesday. There's a Pro D on Friday. I would love to do it on Friday. Otherwise, I mean, it would be great. But it is a redoable quiz, so if you're not happy with your mark on Thursday, you can do it again on Monday, say during flex or something like that. Okay, so just a quiz. 2 versions of the quiz. Version number 1, you will get this column given to you. Except instead of writing malleable or brittle, it will say squishable or breakable. And you'll have to fill in the actual words in the actual columns. Instead of saying ductile, it will say pullable or non-pullable, okay? So in version number 1, so the regular quiz, you get this row. Sorry, column. In the enriched quiz, that column will be blank and you'll fill it in. Okay? Does that make sense? I'll put that up like on Teams so that, you don't have to, find that page on there and it's all squished in there. Okay, so quiz Thursday on this. The other thing that will be on the quiz is you need to be able to draw the staircase. Yes? And you need to be able to shade either the metals or the non-metals. Okay, what was the other thing I was going to say? Oh, yes. The lanthanides and actinides, these guys, are they metals or non-metals? They are metals. Okay, so don't forget about that. The lanthanides and actinides are metals. So if you're shading the metals, you need to shade the lanthanides and actinides. And again, when is that quiz? Thursday. What's on it? The table of properties of metals and nonmetals, and also being able to shade metals and nonmetals. Ooh, you know what else is on there? I just remembered, I'm sorry. Also on the quiz, you need to be able to label the alkali metals, the alkaline earth metals, the halogens, and the noble gases. You need to be able to label the transition metals and the main group elements. So it's basically like this entire first 2 pages of this this sheet, yes? No, 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 no. I'm not sure why I'm writing it here because it'll be much easier for you to find it on Teams, but I don't know, I feel a need to write things down in transition, metals, main, group, elements, and these guys. So groups 1, 2, 17, 18 with their names, so that would be your alkali metals, alkaline earth, halogens, noble gases. Is good? Will be better when it's all written down somewhere nicely for you? Yes. Okay. Don't worry, that will happen. Okay. Basically, yes, but I'll make it better for you later. Like I'll just put it up on Teams so that you know where it is. Alrighty. All of it will be on Teams, all of it, yeah. And I can actually post this entire like sheet. I can print it out and put it up there, yeah. Okay. On our next page, there is a third category of elements in addition to metals and nonmetals, and those are the metalloids. This is on page 64. Sorry about that. Yeah, for sure. Is that the one? Or the one before? That one there? Yeah. Why does it keep snapping to the wrong size? There we go. Okay, how are we doing? Oh, I agree. I just don't know how to do a 2-day weekend anymore. I feel exhausted. I know. So page 64, metalloids, they are found between the metals and the nonmetals on the periodic table. Most metalloids, they look like metals. They are shiny. Okay? So they're kind of like metals. Similar to metals in that they are shiny. However, they are less conductive than metals. In other words, they are semiconductors. They conduct, but not well. They are more brittle than metals. So if you had a metal, it would be shiny and malleable, but these guys are shiny, but they are brittle. If you hit them with a hammer, they will break. They are also typically solid at room temperature. That would be like, is that like metals or like non-metals? Metals, okay, solid at room temperature, which is the same as metals, but it's also the same as some neighboring non-metals. So if we go, you can just stay here. I'll just show you on the periodic table. Not that one. There we go. So here we have our staircase. And our metalloids, we have silicon, we have boron, we have germanium, arsenic, antimony, tellurium, polonium. And one thing I want you to notice is this, at this corner down here, things kind of fall apart. I don't get too excited about who's a metal, who's a non-metal, and who's a metalloid. Do you know why that is? Yes. Pardon me? Yeah, these elements down here, they're super unstable. They're not actually found in nature. They are only found in like particle colliders. Have you guys heard of particle colliders? Physics people doing experimental physics, they'll smash particles into each other and create new things, new elements. That's the only place you find them. So they don't actually stick around long enough for us to actually study them and look at their properties in much detail. So don't worry about what's happening at the bottom right of the periodic table. It's not actually particularly important. But one thing I wanted you to notice is that all of these guys are solids, right? Your semi-metals, your metalloids are solids. But you know who else is solid? Carbon is a solid. Carbon is right beside the metalloids. It's a solid. Phosphorus is a solid. Selenium is a solid. Iodine is a solid. Sulfur is a solid. So you see when you start getting close to the metalloids, the non-metals tend to be solids. Okay? You're not responsible for knowing which non-metals are solids or not at this point. Just kind of get the general idea. Okay? Oops, that's not what I meant to do. Okay, where were we? Two. And number 5, you don't really need to worry about just yet. We'll come across this later, but when we come to the next unit after this one, you'll learn that nonmetals tend to form covalent compounds, which is like nonmetals. So they do some things like metals and some things like nonmetals. They border the staircase. The only one that's not actually, that does touch the staircase and is a metal is aluminum. However, everybody else touching the staircase is a metalloid. Tellurium? Which one? What number is it? 117. Remember what I said about the bottom corner? What did I say about the bottom corner? We don't really care about it because they don't stick around long enough for us to observe their properties. So it's really hard to say, do they behave like metals? Do they behave like non-metals? Do they behave like metalloids? Because we can't study them because they're not there for long enough. You smash particles into one another, and sometimes two of those particles join together and become a larger particle. You would need to ask your physics teacher that because that was not part of my degree. You could ask Mr. McLean, who's in that room there. You could ask your Mr. Denani, who's in that room right there. Or you could ask, what's her last name? Ms. Kaur. Kaur, who's in that classroom there. So 1, 2, and 3. So 313, 309, and 311. Okay, those are our physics teachers. Yes? On this periodic table was made when, like, before I got to this school. So that was, well, it was here when we ordered it, like 2000. And so some of these were not discovered at that point. Okay. But because we use this so seldom, it doesn't really matter that they're not up here. It still makes a good display. Right? Yeah. Yeah, no, it's a good question. Yes. The only new elements we discover are ones that we make. Okay? All of these ones down here are man-made. Okay? So you are responsible for memorizing where the metalloids are. That could also be on the quiz. Ooh, look, I'm adding things all the time. And that their properties are in between metals and non-metals. Do you need to know the specific properties? No. You are not responsible for their specific properties except for knowing that they are semiconductors. And the reason I'm going to make you responsible for that is it is so important for the computer industry, and that is so important to, like, sort of everyday life these days. Because all the microchips are based on silicon and other metalloids. Okay? Okay. I think that's it. I think at this point you could do the questions on page 63. There's number 2 and 3. You could do the questions on page 4. Not page 4, what am I saying? 63, questions on page 63, 65, and 66. If you did not watch the video over the weekend because you didn't find it because I put it the wrong place, that is your other homework. It's only about 10 minutes, okay? That would be 2.1a. Seven minutes and 8 seconds. No, not 2.1a. What am I saying? Oh my God, 2.4a, 4a. There we go. 68 to 70. So folks, when I ask you to shade the metals or shade the non-metals, you can ignore the metalloids. You can just be like, I'm going to shape everything up to that and including things that touch the line. Okay? So metals are to the left, non-metals are to the right. The metalloids will be in a separate question on their own. Okay? And you can skip number 7C because it asks you about something you don't know yet. But I'll come and tell you because you're interested. And I'm setting an alarm for myself to remember to bring in the alkali metals for tomorrow because I wanted to do a demo today. But